Imagine a world where your devices aren't fixed in form, but can dynamically transform their shape and stiffness. This isn't science fiction. It's the imminent reality brought forth by a groundbreaking innovation, a new type of electronic ink capable of creating circuits that shift between rigid and soft states when heated. This revolutionary material promises to redefine the very essence of electronic design and manufacturing, paving the way for a future where adaptability is the ultimate feature. At the heart of this paradigm shift lies a meticulously engineered composite material. This isn't just any ink. It's a sophisticated blend designed for dynamic transformation. Understanding its composition is key to appreciating its potential. The ink primarily combines gallium, a fascinating metal with unique thermal properties, with a specialized polymer-based solvent. Gallium is solid at room temperature, yet it possesses an incredibly low melting point, just below human body temperature, specifically 98.6 degrees Fahrenheit or 37 degrees Celsius. This characteristic is crucial as it allows for a controlled phase transition with minimal thermal input. The polymer-based solvent, on the other hand, is engineered to decompose precisely when gently heated, acting as the catalyst for the ink's transformative properties. The true genius of this electronic ink lies in its functionality, a process that transforms a stable, printable substance into a dynamically conductive and shape-shifting circuit. When the ink is applied and then subjected to a controlled heating process, a remarkable sequence of events unfolds, unlocking its full potential. Upon heating, the polymer-based solvent within the ink begins to break down. This decomposition isn't merely a physical change, it initiates a subtle chemical reaction, creating a slightly acidic microenvironment within the ink. This acidic condition is critical because it effectively removes the thin, naturally occurring oxide layer that typically forms on the surface of gallium particles. Without this oxide layer, the individual gallium particles, now reaching their melting point, are free to coalesce. They merge seamlessly, forming continuous, highly conductive pathways that constitute the functional electronic circuit. This transition from discrete, non-conductive particles to a unified conductive liquid metal network is the core mechanism enabling the ink's electrical functionality and its ability to change stiffness. The innovation extends far beyond mere conductivity. The resulting substance is not only stable and printable, but also possesses an unprecedented ability to dynamically alter its physical properties. This is where the true power of this electronic ink becomes apparent, offering a level of adaptability previously unattainable in electronics. Once the circuit has been formed and made conductive through the initial heating process, its stiffness can be precisely controlled based on subsequent temperature variations. When warmed, the gallium within the circuit transitions back to its liquid state, causing the material to become significantly softer and more compliant. Conversely, as it cools, the gallium solidifies, returning the circuit to a more rigid state. This reversible phase change allows for on-demand manipulation of the circuit's mechanical properties, enabling it to shift between rigid and soft states. This dynamic control over both electrical conductivity and mechanical stiffness opens up entirely new avenues for device design, moving beyond the limitations of fixed form electronics. The implications of this shape-shifting electronic ink are profound, promising to revolutionize numerous sectors and usher in a new era of adaptive technology. Its unique properties make it ideal for applications where traditional rigid electronics fall short, offering unprecedented flexibility and integration. One of the most impactful applications lies in the realm of medical implants. Imagine a pacemaker lead or a neural interface that can be inserted in a rigid, precise form, then soften and conform perfectly to the delicate tissues within the body, minimizing discomfort and improving long-term biocompatibility. This could lead to less invasive surgeries, more comfortable prosthetics, and smart implants that dynamically adjust to physiological changes. Beyond implants, this technology could enable advanced flexible robotics. Robots could be designed with limbs or grippers that can stiffen for powerful manipulation and then soften to navigate tight spaces or handle delicate objects without causing damage. This opens doors for highly adaptable industrial robots, search and rescue bots, and even surgical robots with unprecedented dexterity. The potential extends to wearable technology and smart textiles. Envision smart clothing that can stiffen to provide ergonomic support during physical activity, then soften for maximum comfort during rest. Displays could be integrated into fabrics, folding and unfolding seamlessly with the garment. This ink could also enable adaptive structures and smart surfaces, where entire walls or furniture pieces could change their rigidity or even their embedded electronic functions based on environmental cues or user needs. Furthermore, its compatibility with conventional manufacturing techniques like screen printing and dip coating is a game changer. This means that large-scale production of these dynamic electronics is not a distant dream, but a tangible possibility, facilitating the rapid development of complex, 3D-printed electronic systems with integrated adaptive properties. Beyond its transformative capabilities, this electronic ink also boasts impressive technical specifications, demonstrating its viability for high-performance applications. Its ability to produce fine features and undergo significant mechanical changes underscores its potential for sophisticated electronic designs. The ink can produce features as small as 50 micrometers. To put this into perspective for tech enthusiasts, 50 micrometers is thinner than a human hair and comparable to the trace widths found in many conventional printed circuit boards. This level of precision means the ink can be used to create intricate and high-density circuits, not just simple, large-scale components. Furthermore, rigorous testing has shown that the material can become over 1,400 times softer when warmed. This dramatic change in stiffness is crucial for applications requiring significant mechanical compliance and adaptability, allowing for a wide range of dynamic responses from a single material. This combination of high resolution and extreme mechanical variability positions the electronic ink as a truly versatile platform for next-generation electronics. The development of this electronic ink represents a significant leap forward, primarily by overcoming long-standing challenges associated with liquid metal printing. Historically, working with liquid metals for circuit fabrication has been fraught with difficulties, particularly in achieving stable, high-resolution structures at room temperature. The core achievement of this innovation lies in its ability to enable the room temperature fabrication of high-resolution, large-area circuits that possess adjustable stiffness. Previous attempts often struggled with issues like oxidation, poor adhesion, or the inability to maintain structural integrity during phase changes. This new ink formulation addresses these challenges head-on, providing a stable, printable medium that only becomes conductive and dynamically adjustable after a controlled thermal activation. This breakthrough means that complex, adaptive electronic systems can now be manufactured using conventional, scalable techniques without the need for specialized high-temperature environments or complex vacuum systems. The result is a material that promises to lead to smart devices, offering an unprecedented blend of high performance, ergonomic comfort, and dynamic adaptability, truly blurring the lines between hardware and fluid form. This electronic ink is more than just a new material. It represents a fundamental shift in how we conceive and interact with electronic devices. We are moving beyond the era of rigid, static hardware into a future where electronics are inherently dynamic, responsive, and integrated seamlessly with our physical world. Imagine devices that can literally adapt to their environment, their users, or their specific tasks. From medical devices that conform to the body's intricate contours, to robots that can change their physical properties on the fly, to wearable tech that feels like a second skin, the possibilities are boundless. This technology empowers designers and engineers to break free from the constraints of fixed form factors, enabling the creation of truly intelligent and intuitive systems. The ability to print high-resolution circuits that can dynamically change their stiffness and shape opens up entirely new design paradigms, fostering innovation in fields ranging from advanced manufacturing to human-computer interaction. This is not just an incremental improvement. It is a foundational technology that will underpin the next generation of smart, adaptive, and truly integrated electronic systems. The future of electronics is no longer rigid. It's fluid, dynamic, and incredibly exciting. This electronic ink is just the beginning of a new era where devices adapt to us, rather than the other way around. What groundbreaking applications can you envision with shape-shifting electronics? Share your most innovative ideas in the comments below. Don't forget to like this video, subscribe to our channel for more deep dives into cutting-edge tech, and hit the notification bell so you don't miss our next exploration into the future of innovation. Let's collectively push the boundaries of what's possible.